Alright, so in this video we go over section 5.3 differentiation of logarithmic functions. This will add more tools to our differentiation rules. And these new tools are to differentiate functions of natural logarithmic functions, at least in this section. And well, in this case we can have two different cases for differentiating logarithmic functions. The really basic case when we differentiate 1 over the ln of x, whose derivative is simply 1 over x. However, when this logarithmic function is composite, what we do, that is, this u could be just any other, expression depending on the variable, in this case x. So that's 1 over whatever that u is, and in this case times the derivative of that quantity inside parentheses of the logarithmic function. That is, so let's look at some of the examples. So let's find the derivative of each function for letter A. Notice that we have a sum of two functions. So number one, the derivative of x cubed plus the derivative of ln x. So in this case, we're going to combine two rules. So number one, the general power rule. The derivative is 3x squared, and the derivative of ln x is simply 1 over x. And that's the derivative. For letter B, y equals x cubed ln x. So y prime equals, in this case, well, notice first of all that we have a product of the functions. It would be a good idea to recall what the derivative with respect x of a product u and v is, and that is u prime v plus v prime u. In other words, the derivative of the first factor times the second factor plus the derivative of the second factor times the first factor. So it will be 3x squared ln x, and then plus the derivative of ln x, which is 1 over x times x cubed. And we are essentially done with the calculus part of the problem. However, you might want to simplify this a bit further. That's going to give us 3x squared ln x. And in this case, notice how this becomes a 2 and cancels 1 power of x plus x squared. And that's an okay final answer. Of course, you could factor out the x squared if you prefer. That's fine. Just in case, why not? Let's go ahead and do that. Like x squared times 3 ln x. Erase this. Plus 1. That's another way to write this answer either way. For letter C, so this is one for which we're going to use the chain rule, because notice we're going to differentiate ln of some polynomial, not just ln of x. In this case, for example, so the derivative y prime will be 1 over u, but in this case u equals to x squared plus 2x plus 10, but in this case times the derivative with respect x of the quantity x squared plus 2x plus 10, as it is shown here in what I would call, this is like the chain rule version of the ln rule for differentiation. That is 1 over the u times the derivative with the u with respect x. And all we have to do in this case is differentiate this polynomial. That's going to be 1 over x squared plus 2x plus 10 times 2x plus 2, and we can rewrite this as 2x plus 2 over x squared plus 2x plus 10, and that's the derivative of this function. So as you can tell, I mean, all we are doing is going back to the differentiation rules. For letter D, what about letter D? So be careful with this one, just so you don't overwhelm yourself with the amount of work that you could potentially do about it. So number one, we have a radical right here, and for which, well, I'd rather rewrite this function as ln of x squared plus 3 and then the whole thing to the 1/2 power. And okay, let me do this on the side. Let me do on the side what you are not supposed to do. So, okay, what is it? Plus 3. All right. So the derivative of ln of x squared plus 3 to the 1/2. So this is what you might be thinking of doing. 1 over x squared plus 3 to the 1/2 times the derivative with respect x of x squared plus 3 to the 1/2. Well, I mean, it's still valid to do this. However, you would have to do a chain rule when differentiating this function right here. And well, yes, that's fine. That's still doable. There's nothing wrong with that. However, we're going to simplify a lot of the work by using the properties of logarithms that you might have reviewed in one of the other models in which I covered those laws of exponents. And let me write this down. Whenever you have ln of a to the n power, this is n times ln of a. So what we do in this case essentially is this n becomes a coefficient, you know, and that's the ln rule that we use. Well, that's what I'm going to do here. 1/2 ln of x squared plus 3. All right. So this is not calculus yet. This is only algebra. So we are using the properties of logarithms so we can take the derivative of the function in a more easier way. So let's find the derivative now. So that's y prime equals 1/2 times, notice in this case we have some ln of u, so that is 1 over the quantity u, which is x squared plus 3, times the derivative with respect x of the quantity u, which is x squared plus 3. And in this case, well, what's that going to be? So we're going to have 1/2 times 1 over x squared plus 3 times the derivative of x squared plus 3, which is 2x. But notice something here. Notice how these 2's are going to cancel. And we're going to end up with x over x squared plus 3. And that's final answer. All right, let's have a look at other examples. For the next example, y equals ln of 1 plus ln. So that's going to be a composite function. That means we will use the chain rule. So in this case, take the derivative y prime equals, okay, notice that we have ln functions, but in this case we have an outermost ln and then an innermost ln. So in this case, we're going to use the not the general power rule, but the chain rule. That is 1 over the quantity in parentheses, which is 1 plus ln, times the derivative with respect x of the function 1 plus ln x. So let's take the derivative of this quantity in parentheses. And then that times the derivative of 1, which is 0, plus the derivative of ln x, which is 1 over x. And 1 over x plus 0 is simply 1 over x. And in this case, that's 1 plus ln x times 1 over x. But I would strongly suggest that you rewrite this answer in the following way. So in this case, multiply across 1 times 1 to give us a 1. And in the denominator, think of this quantity 1 plus ln x as having parentheses. And that's going to give us x ln x. Oh, not ln yet. One plus ln x. And that's final answer. So now that we have done a couple of examples involving, what did we do? Well, the general, okay, product rule, chain rule, a couple of chain rule problems. Let's do one that involves the quotient rule, and let's recall what the quotient rule is. So the derivative, the quotient u over v, that will be u prime v minus v prime u. Notice for the quotient rule, this is a minus over the denominator squared. All right, so that's the quotient rule. So we can differentiate this guy right there. All right, so okay, let me change this to a prime instead. Yeah, much better. So in this case, let me change the notation to dy dx. Well, just to use different notations for the derivatives. So in this case, it's the derivative of the numerator. The derivative of the numerator, which is 2x, that'll be 2x, but times ln x plus 3. And then, or not plus, but rather minus the derivative of ln x plus 3. Well, the derivative of ln x is simply 1 over x. The derivative of 3 is 0, so that's simply 1 over x times the numerator x squared. And then the whole thing being divided by ln of x plus 3 quantity squared. So of course, over here there's a lot of room for simplification. We can cancel x squared over x, leaving us with simply an x. So that's going to be 2x times ln of x plus 3, and then minus x. And this could be an okay final answer, or we could factor out the x's. It's up to you. We could leave it like this. That's fine. That's good enough. Or, yes, we can leave it like this. That's good enough. I mean, factoring the x is not going to help us cancel anything else any further anyway. Okay. However, well, I'm just going to do it on the side. So this would be the same as 2, no, not 2, actually we're factoring the x times 2 ln x plus 3 minus 1 over ln x plus 3 squared, and we could distribute the 2 over here, and that's going to give us x times 2 ln x plus 6 minus 1 over ln x plus 3 quantity squared, and finally x times 2 ln x plus 5, because 6 minus 1 is 5, ln of x plus 3 squared. As you can see, factoring out that x doesn't really help us cancel out any powers of ln x plus 3 or make this expression any simpler. But either way, you can do it. You can choose to factor out that x or leave it in the form I left it before. Alright, so letter G. Look at this madness right here. So ln of x squared plus 5, the quantity cubed, times the square root of x squared minus 2x divided by 2x minus 5 ln of x. So, alright, what are we supposed to do? Y prime equals to 1 over x squared plus 5 cubed root of x squared minus 2x over 2x minus 5 times ln x times the derivative with respect x of this whole madness. No, we're not supposed to do that, because think of the amount of work that we would have to do if we did it this way. We would have to do with chain rules, with product rules, with quotient rules, and well, combining all that, it's just going to be madness. So this is what we're going to do. We're going to look at the properties of logarithms, which I'm going to list over here. I'm going to list the natural log of AB is the natural log of A plus the natural log of B. That's the product rule of logarithms. And another property is ln of the quotient, A over B, that's ln of A minus ln of B. And C, the other one, ln of A to the m, that, or n rather, that's n ln of A. You know, and I already mentioned letter C in the previous page. And this, for more details about the properties of logarithms, you might want to go back to the model from the week before so you can review what about these properties of logarithms before looking at this example. Once you do that, if you believe that you need more review on this one, well, you may go back to this example. So what we're going to do in this case is rewrite this ugly looking function into a lot more simpler functions to differentiate. That is, I'm going to use algebra here to simplify this natural log function. So in this case, I'm going to use first of all the quotient rule. That's going to give us ln of x squared plus 5 cubed square root of x squared minus 2x minus ln of 2x minus 5 times ln of x. Alright, and then from here, I'm going to break each term into using the product rule. At the same time, I'm going to change this, this radical form into rational exponent. That is, what we're going to do here is ln of x squared plus 5 to the third power plus ln of x squared minus 2x, the whole thing to the 1/2 because the square root means 1/2 power. And then minus, when I write a minus, I need to make sure that I have ln of 2x minus 5 plus ln of ln x. Alright, and then I'm going to use this negative sign to distribute over here and change the sign of everything inside of the brackets. That's going to give us, okay, on the one hand, I will also do another properties of, well, the properties of logarithms, in particular, this one right here, the power rule or the smackdown basketball rule, which is what I mentioned that on the review videos. So this one becomes a coefficient, this one becomes a coefficient in the same way I did it in another example in the previous page. So this will be 3 ln of x squared plus 5 plus 1/2 x squared minus 2x minus ln of 2x minus 5 minus ln of ln x. And yes, we have many terms here to differentiate. However, these are a lot more simple to differentiate. So this is what we're going to do. So now that we did a few derivatives using the chain rule, I will just go ahead and go like y equals to 3 times 1 over x squared plus 5, and then times the derivative of x squared plus 5, which is 2x, plus 1/2 times 1 over x squared minus 2x times the derivative of x squared minus 2x, which is 2x minus 2, minus ln, the derivative of ln of 2x minus 5, that's 1 over 2x minus 5 times the derivative of 2x minus 5, which is 2. And last but not least, the derivative of ln of x, that's 1 over ln x times the derivative of ln x right here, which is 1 over x. Okay, be careful how we combine this lx with ln x in the denominator. Okay, let's do one at a time. So that's going to give us, okay, over here, 3 times 2x, that's going to give us a 6x. This was supposed to be y prime. So that's a 6x over x squared plus 5. Alright, and also see what's going to happen here. This 2x minus 2 right here, it's going to be 2 times x minus 1. And that 2 right here is going to cancel with the 2 in the 1/2 in the front. That is x minus 1 divided by x squared minus 2x. And over here, let's just multiply across 1 times 2. That's going to give us negative 2 over 2x minus 5. And last but not least, be careful again, how do we combine these two together? When we multiply ln of x times x, this is not ln of x squared, because really what we have here is parentheses around this x that we don't, I usually don't write them when it's only ln of x, but it's understood that they have to be there. So in this case, what we do is simply have the x in front of the ln of x. Alright, and this is final answer for this exercise. And this is something that you might want to try when you have logarithmic functions of something a little bit more uglier, you know, like other examples that you might see in the homework, like ln of 3x plus 5 times, I don't know, 7x minus 3. No, you don't want to do 1 over boom boom and times the derivative of this whole thing as a product rule. No, you don't want to do that. Instead, what you want to do to make your life easier right here, break it in the form of two terms, ln of 3x plus 5 plus ln of 7x minus 3, and then take the derivative of each individual term instead, in the same way that we did for this example. That being said, this is it for this section. I'll see you in the next video.